All right, so let's get started here. I think I should mention test 5. Is take home. And so I will post test 5 on Monday. So now I think the syllabus kind of indicates maybe this Wednesday or something, but I think next Monday is what, I forgot, 24, 25? Yeah.
We gotta write it out and rank these?
Yep.
Okay.
So you should print it out and
Can I just write it out?
yeah, you can just write it out. That'll be okay.
Make sure it's very easy.
It'll be neat and in order. I think that works for me. Let's see here. Calendar. Yes, 25th. So it'll be, well, actually, so it wouldn't be due the 25th. It would be due 27th, yeah. So this is when it's due. It'll be due via Blackboard. Actually, I'd prefer to get paper copies, honestly. So let's say due in person. 11. No, when does this class start? 11? What's wrong with me? 12:20? So, and I will post it. I'll post it on Monday if all goes as well. The 25th. Right. And I will email once I do that. Right. So there will be no review sheet for this one. It's just going to be the test, but okay. But got a little bit more to cover here, of course, before this, because the test 5 is also covering chapter 7. So I'd like to try to wrap up what I have to say about chapter 6, and hopefully start on some chapter 7 today. Yeah. Now we did already actually cover chapter 7 material in a way earlier in the course, but anyway. All right. So I hope you all had a chance to watch the video from last year. The math hasn't changed, right? So, although now I've gone to chalkboard rather than whiteboard, since last year this thing was like the bottom of the board was here. So I can't write on a board that's like. And then I asked them to lower it a foot. I think they lowered it more like 16 inches, because now it's like, this is like the shortest chalkboard anywhere. But yeah, I actually kind of like it. Okay, so example 1. Let's solve the square root of 2x minus 3 equal to 4. So to solve this, we square both sides, right? That gives us 2x minus 3 equal to 16, which gives me 2x equals to 19, which then gives me x equals to 19 over 2. So, there you go. Doesn't have to be hard, does it? Let's see here. Let's look at example 2. This one will be the cube root of x plus 5 equals to 2. All right. So when we're faced with a cube root, what we want to do is cube both sides. So we cube it. And that gives me x plus 5 equal to 8. So x equals to 3. So the homework's like this. So it wasn't
It's a little more difficult.
a little bit more difficult. Yeah, let me try to make it more difficult.
There was one,
Mm-hmm.
I don't know, I had to use photo math on it, but I could not figure it out.
Had to use photo math on it.
It was like, I don't remember the numbers, it was like, let's see,
Uh-huh.
equals square root 2x minus 3 equals square root of something else.
Right. Oh yeah, I'll do one of those. One with 2 square roots in it. Yeah, I'll get to that. Let me do this. This working our way up the chain here. This one. Again, it's pretty nice. The radical's already isolated, so you just square both sides to solve it. Now this squared gives me x squared minus 14x plus 49, x minus 5, which gives us x squared minus 15x plus 54. Since this problem's from the book, I believe in my heart this will factor. Did following my heart work here?
Right in the bottom first.
What's that?
Which one are you factoring?
This one?
Or-
Yeah, factoring that would not help. What's 54 is what? 6 times 9? There it is, like minus 6.
I didn't think of that.
Yeah, yeah. So, answers are 6 and 9. Now we need to check those. So like, is 6 minus 7 equal to the square root of 6 minus 5? Is 9 minus 7 equal to the square root of 9 minus 5? Well, this gives me minus 1 equals to is 1. And this gives me 2 is equal to the square root of 4. So we have a winner. So this is this. No. So no, that one's extraneous. The answer here is x equals to 9. So anytime we work one of these where we square the problem, we get 2 answers, we have to go back to the start and check. Otherwise, we can trick ourselves into thinking that we have a solution that's not actually a solution. If you were to solve the problem, 7 minus x, see, 7 minus x equal to the square root of x minus 5. This one, right, this has x equals to 6 as a solution. Right? And you notice that the green problem I just wrote and the white one we started with, when you square both of them, what happens? They both go to the same next step. So they both give to the same, both give you the same quadratic, and that quadratic equation gives you the answer for the problem that was stated, but also for the other problem which was not stated. Because once you square, you lose track of what was minus before the square. And that's why we end up adding solutions that aren't really solutions, they're extraneous. So just something to watch out for. Let me try, here's one of those ones with the root and the root. Root and root. Try work. I'll make sure to put one of those on the test then. So you like a challenge, right? No?
Not in math, I don't like that.
I was going to say, why are you in the road? Why involve? If you don't like challenges, why are you in the rodeo? No.
Why that kind of challenge? You got the fast. This.
Right. Math, you don't lose in the real life. But like staying on a horse, as long as you can, that's definitely like a real world thing. right? It's just something you use in your everyday life all the time. Like, I'm going to the grocery store, and they said, if you want to check out, first you got to ride this horse, right? Like, you're like, the rodeo's in the real world. It's a real world application. In the same way, real people will take my tests. Therefore, math has a real world application. All right, I'll shut up. All right. How about this one? Square root of x minus 9 plus the square root of x equal to 1. We'll work that one. And then next one.
That's not what I was talking about.
No?
No. Put an equal sign in between where the plus sign is. That's what was on the map.
You mean you had something like, there was an equal here?
Yes.
So it looked more like, let's say 4 plus square root of 10 minus x equal to, say, 6 plus the square root of 4 minus x.
Yes, that's what it looked like.
Like one of these. Okay. We'll get to that one. Working our way there. So again, but both of these actually, and the story always, first of all, isolate the radical, right? So square root of x minus 9 equal to 1 plus root x. I square both sides. And I would say isolate the ugly radical too, because you want to get rid of the ugliness as fast as you can. So that does that here. And I mean, yeah, you still got a radical x left over, but at least you're not writing the square root of x plus 9 a bunch of times. Right, so we've got, that gives me an x, of course, right? So I've got, fine, I'll write it out. Notice that this and that cancel, right? And that leaves us with 2 square root of x is equal to minus 10.
Would the 2 square root of x cancel out?
There's not 2 square root of x's though. Oh, I would, if I cancel, I could cancel this and that, but that would not be,
Okay.
I mean, yeah, that would just give me 0 equals 0, which is true, but useless. But this, see, I've subtracted the 1 over here. I mean, I'm keeping the 2x, I'm subtracting the 1 to the other side. That'll divide by the 2. Square root of 2x equals to minus 5. See, whenever you see something like this, you stop right there. Stop right here. This, impossible. See, because why no solution? Because the square root of x is greater than or equal to 0, whatever you put x. So I can't have the square root of x equal to minus 5. Now, when you square this equation, you'll get plus or minus 5 as solutions. And then you'll get 25 as a solution, rather. But 25 doesn't work because the square root of 25 is 5, not 5 is 5. Right. So no solution is the answer to example 4.
And nowhere in the homework had greater or equal signs, did you?
The what?
In the homework, like the greater than or equal to signs? None in homework.
Oh, well, that's just, I'm just making a theoretical comment, you know.
I didn't know if that was like going to be on the test.
Oh, well, I'm just saying that, but no solution was in the homework, right?
Yes.
Yeah, so that, I'm saying this is why there's no solution, because we can't have this being true and this at the same time. Like, you know, it's not simpatico. Now, isolate your radical, whichever one you want. I'm gonna isolate the square root of 10 minus x. So that gives me 2 plus the square root of 4 minus x, yeah? I square both sides. That gives me 10 minus x. 2 times 2 is 4. plus 4 square root of 4 minus x plus the square root of 4 minus x squared, which is again 4 minus x. Oh, look at that. That's nice. See this? And that? All right, great. So that's out of the picture. And we got what? We've got 4 square root of 4 minus x equal to 10 minus 4. Well, there's 4 plus 4, right? That gives me an 8. 10 minus 8 is 2. Then divide by 4. As square root of 4 minus x equals to a half, yeah? Now again, square. This gives me 4 minus x equals to 1/4, which gives me x is equal to 4 minus a quarter, also known as 16 minus 1 over 4. So I believe we get 15/4 as the answer. And then, of course, we should go back up to the top and check it just to be safe, you know. But you can check it, it'll work. Any questions? Now, there doesn't always have to be just one answer from these. There can be 2. There can be none, right? Example 6. Square root of 6x plus 7 minus the square root of 3x plus 3 equals 1. All right. So which one, how would you go about solving that one there?
Isolate the 6x plus 7.
Isolate the 6x plus 7. Okay. So we got square root of 6x plus 7, 1 plus the square root of 3x plus 3. Square both sides. 6x plus 7, 1 plus twice that, plus the square of this, which is that again, the radicand, right? Now this time, this and that don't cancel like they did in the previous 2 examples, but this is going to, we isolate the radical again, right? So we've got 2 times the square root of 3x plus 3 equals 2. So I'm going to bring everything here over to there. I'm going to write it there, though. So like 6 minus 3 is 3x. So I have 7 minus 1 minus 3. That's 7 minus 4, which is 3. Yep, square it again. Now, I've been dividing by the 2, but you don't have to do that. You can leave the 2 in place and you can just square it. That way you won't have to work with fractions. So that's kind of a, you know, just a comment. You don't have to divide by, you don't have to isolate the radical entirely. It's like, it's enough to get it a number times the radical. That's fine. It'll still work out nice for you when you square it. Because we'll get, but you do have to square the 2. So 2 squared is 4, right? And then you get 3x plus 3. And then over here, we get 3 times 3, which is 9x squared, plus 6 plus 12x, as it is, plus 9. And then, well, this is actually kind of nice because, really? Huh. So 12x plus 12 funny. Just a second. It feels wrong. Mostly because I looked at the answer when I copied the problem down. And so I knew I have a memory of the answer, which doesn't seem consistent with where I'm going. I think this was number 40 in section 6.6. Square root of 6x plus 7 minus the square root of 3x plus 3 equals to 1. Yeah, okay, all right. Just a second here. Let me sort through this. All right, let me just keep going. Maybe I'm thinking too hard here. So these cancel. Right? And then I get 9x squared, right? Minus 3. Equal to 0. Right? And, yeah. And, well, the book says that the answers are -1 and 1/3. No, that shouldn't matter. Shouldn't matter. I mean, that's a legitimate step. I mean, I'm not in doubt about that. Maybe the answer in the back of the book. Maybe the book might be wrong. I mean, it's possible. So if I this gives me 9x squared equals to 3, which gives, I think there's a simple way to understand why the book is wrong. That's 3 over 9, which is 1/3. Oof. Ooh. Well, I'm getting x is equal to plus or minus 1 over root 3. Let me see if the book is right. So the book said that the answer was x equals to -1 or 1/3. I mean, we can figure out if I made a mistake by just trying the book's answers, like checking them, yeah? So what happens if we plug it in here? Does it actually work? Let's start with a -1, right? So square root of -6 plus 7 minus the square root of, -3 plus 3 equals 1. Well, that's good. That works. And if I plug in 1/3, the 1/3 gives me 6 over 2, which is 6 over 3, which is 2. 2 plus 7 is 9. So square root of 9. And if I put in a third here, I get 1 plus 3, which is 4. So 3 minus 2 is 1. These are right. Okay, so I have made a mistake in my algebra. Oh, here it is. Look. It's right here. When I square 3x plus 3, right, I get 3x times 3 plus 3 times 3x. What's 3 times 3x? It's not 6. It's 9. So it's 9 plus 9. See, this is supposed to be 18. That's the problem. And so these don't cancel. I told you that felt wrong when I did it, didn't I? So that's an 18, which then gives us 9x squared, subtract 12, plus 6x, yeah, minus 3. So divide by 3. And then I think we can factor this. So you got plus or minus 1 to get a minus 1 because it's a book problem. And so I guess we do plus 1 here, we do minus 1 here. So that gives me minus x plus 3x, which gives me 2x. And this, of course, corresponds to the solution minus 1. Excuse me, minus 1 from this one and 1/3 from that one. 3x minus 1 equal to 0 means x is equal to 1/3, right? All right. Okay, so I think that's quite enough for chapter 6, this part of chapter 6. Now I'm going to go over to section 6.8, which is on complex numbers. Was there homework on complex numbers? See, there might not have been.
I think it's not the 6.7, but 7.1 and 7.2.
Is that right?
Show me an example from 6.8. I'll tell you.
7.1, 7.2, quadratic formula. Well, that seems reasonable, but see, the quadratic formula has I in it, right? So I think it's healthy for us to talk about section 6.8, yeah?
I think they just threw section 6.8 and 6.7 in together because there's like 25 questions on that one.
Oh, okay. Well, whether or not this is directly on the homework, it will directly help us in being confident about doing the quadratic formula, all right? So let's look at it from that perspective at least. Okay, so complex numbers. What is a complex number? So a complex number has the form z equals to x plus iy. We say the real part of z is equal to x. The imaginary part of z is equal to y. All right? And the neat thing is, if we have, we also talk about complex conjugate. So z conjugate is x minus iy. All right. The neat thing is, if you multiply z by z conjugate, what happens? So you get, by the way, I should probably tell you, I squared is minus 1. All right. So if you want, you could think of I as being the square root of minus 1. Okay. Now, obviously that's not a real number, right? There's no real number whose square is a negative number. It's not a property of real numbers. So this is something different, something new. If we multiply this out, though, what we get is x squared plus iyx minus ixy minus I squared y squared. And so these guys cancel. And what we're left with is x squared plus y squared. So if you picture this number in the complex plane, so complex numbers can be visualized as a plane, right? The distance of the complex number from the origin is what? What's the distance from here to here? Square root of x squared plus y squared, right? This is the Pythagorean, this is a distance formula, right? And of course, you could write that as the square root of z bar if you want. So this actually has a special notation. When you study complex variables, we use what's called the absolute value of z. It's defined to be this, the absolute value, or as it's sometimes called, modulus. Anyway, it's the length of the complex number, right? Well, something pretty cool happens here. Notice that z bar, so z bar is x squared plus y squared, right? So if we solve this, we could solve this equation for 1 over z. What's to say 1 over z is equal to? So suppose this is not equal to 0, okay? For the purpose of discussion, what if you solve this equation for 1 over z? Well, we could do like, just flip both sides, right? Like 1 over z bar equals 1 over x squared plus y squared, right? So 1 over z is actually equal to what? It's actually equal to z bar over, x squared plus y squared. Or another way to look at it, it's just z bar over z bar. So if we want to calculate the inverse of a complex number, there's a simple kind of trick to do it. You can multiply, you can divide z bar by z bar. Let me actually put this into practice here. So what I mean by calculate the complex number, I really mean you can find what's called Cartesian form of the complex number. So the Cartesian form is what I just erased. All right, so example 7, 8, I don't remember. When I ask my son this, he always tells me 20. So there, in honor of Daniel, example 20. So if I had z equal to 2 plus 3i, and I want to find the Cartesian form of 1 over 2 plus 3i, what I do, just like we were doing the rationalizing the denominator before, same trick. But this time we do, so I do 2 minus 3i over 2 minus 3i, like that. And so this is z times z bar. It's always just the square of the real plus the imaginary. So this is going to be 2 minus 3i over 2 squared plus 3 squared. Which is 9 plus 4, 13, right? So this is 2 over 13 minus 3 over 13 times I. So like any complex, like a reciprocal of a complex number, we can always find the Cartesian form of it by multiplying by the conjugate over the conjugate. This is the analog of the rationalizing denominator calculation for complex numbers. It's the same song and dance, really. Example 21. Complex numbers are weird. Check this out. So 1 plus I, what happens if I square that? So I'll write it out. So this is 1 times 1, which is 1, plus I, right? Plus I squared, right? I squared is minus 1. So that means that this and this cancel. 2i. So I don't know, like, just at first glance, that's weird, right? Like, you have something that's got a real and imaginary part, and yet when you square it, It just has an imaginary part. It's interesting. Show you another example here. Let's see if I can do this one right. Let's play some games. Now this isn't so much a cautionary tale about imaginary numbers. Well, it is partly, but let's see here. So 1 is equal to minus 1 times minus 1, right? We agree? Minus 1 squared is 1. All right. So the square root of, so 1 is the square root of 1, right? So it's the square root of minus 1 times minus 1. Right? Yeah. And so that is the square root of minus 1 times the square root of minus 1. Which is I times I, right? Which is minus 1. But I think where I come from, like 1 is not equal to minus 1, right? This says 1 is equal to minus 1. What gives? I mean, we can't have 1 equals to minus 1. That's just a contradiction to math. The thing that's wrong, all right, the step here that's sketchy, is right here. This step, right here. No. You can't do that. It is not a property of the square root function. It's like the square root of the product of minus 1 and minus 1 is not equal to the product of the square roots. We have to have positive numbers when we do that. So like the square root of AB is the square root of A times, let me write it out. So square root of AB is square root of A times the square root of B. That assumes that A and B are non-negative. All right? If you're going to work with the square root of negative numbers, you have to develop a little bit more theory to understand it. Like you can't just work with the one, your square root has to be replaced with a set of square roots. And so like there's a way of understanding this in the complex analysis class, but obviously that's not something I should share here, right? My point to you is there's a context for the rules of algebra, and if we extend past that context, we get into trouble. So, but that said, we can do many, many things with complex numbers, which are just like usual. They have the same basic rules of algebra. They commute, they're associative, the distributive property still holds, like everything holds, except that I squared is minus 1. And I say everything holds, that's not exactly true either. Like the inequality stuff we do, like 3 less than 5. We can't do that with complex numbers either. Like if I said, I've got 1, I've got I, which one's smaller, 1 or I? That question's not meaningful. Like there's no ordering of complex numbers in the same way that there's an ordering of real numbers. There's no ordering of the complex numbers which respects the algebraic properties of the complex numbers. That much I can say without hedging. Let's see here. So another example. This is another thing that kind of, if you're not aware of it, it'll really get you. Example 23. If we have 1 over I, what's that equal to? So if we use the trick, right? We should do, this is what? Minus I over I times minus I, right? Which is minus I over what? Minus I squared. What's minus I squared? Minus I squared is minus 1. Oh, minus I squared is plus 1, because it's minus minus 1. So minus I. Now this is like completely unsurprising if we just take a second and look at it. So like I times I is equal to minus 1, right? So that means that 1 over I is equal to minus I. Like you can get from here to here just by, say, divide by. It's easier if I put the minus on this side, yeah? So then just, divide by I. There it is. So this is weird, right? The reciprocal of I is minus itself. Okay. Now there's all sorts of really interesting things to ask about here, like what is the meaning of complex multiplication? So those things are very fun to think about. You can pretty easily convince yourself that if you multiply a complex number by I, it rotates the number by like 90 degrees. If we could talk about rotations and angles. But we shouldn't do that in here because, of course, as you know, there is no trigonometry in this course. So I will cease and desist from my comments on that. All right, so in the time that remains here, which I think I've got 5 minutes. I think I've got 2 minutes. I will point out to you, if we have x squared, ax squared plus bx plus c equal to 0, then what we'll prove next time is that this has solution x equals to minus b plus or minus the square root of b squared minus 4ac all divided by 2a, right? This is the chapter 7 quadratic formula, right? But to make sense of this, it's possible that the discriminant is the b squared minus 4ac term, the radicand here. If that's negative, this is a complex value, right? The derivation to go from here to here is completing the square. This is by completing the square. So I'll talk about that story next time. And hopefully next class we'll pretty much finish the story of chapter 7. So I don't think we'll have an in-class meeting this Friday because of rodeo.